It has been requested, ladies and gentlemen, that I do a video to review for the upcoming test. The content of this test, to remind you, is over limiting reagents, percent purity, and percent yield. I'll talk about all three of these, give you an example of them, and hopefully this will help you out. Percent yield. Let's start at the beginning. How about limiting reagents? Limiting reagents, ladies and gentlemen, if you remember, is just the reagent or reactant, the same thing, that holds you back. It's what's going to run out before anything else. When you run out of one of your reactants, the process is over. So you need to know which one is going to run out first. The other reactant is called the excess reactant. It doesn't matter how much of that you got. You're not going to use it all. So we need to be able to find the limiting reactant given a situation. First, we would have a chemical reaction on the board. Something like this. What if I had some calcium hydroxide and I reacted it with hydrogen chloride to make some calcium chloride and some water. First, you need to know if the equation is balanced. That's our first move always. Calcium, there's one there, one here. We're good. Oxygen, so two right here. So two oxygens, only one right there. We're going to need to increase this. Now my oxygen's fine, but I have 4 hydrogen right there, and a total of 3 over here. What if I put a 2 right here? Okay, that fixes our hydrogen problem. And it also fixes our chlorine situation. We got 2 chlorines, so now we're all balanced. We're good. What if I said we had 6.3 moles of of HCl, and we had 2.8 moles of calcium hydroxide. Which one's the limiting reagent? Whichever we have less of. And ladies and gentlemen, we have to compare moles. It has to be moles. Have to be comparing moles. If I give it to you in moles, that's great. Easy comparison. This right here would be our limiting reagent because we have fewer. 2.8 is less than 6.3. But if I give it to you in grams, that is a little bit more hairy. What if instead of I give it like this, what if I said, oh, I don't know, you had 5 grams of HCl and 10 grams of calcium hydroxide. You may say, oh, Mr. Wallace, this is less, so it must be it. No. You've got to compare moles, not grams. Atoms and molecules have different sizes, so that doesn't work. Have to compare moles. Let me show you how you do that. We are going to have the 5 grams here, going to convert that to moles. These are different color pens, which is quite clear. 5 grams of HCl times, we're going to put whatever's here goes down here, grams of HCl, and 1 mole of HCl on top. So we need grams here. What is the molar mass of hydrochloric acid? Of hydrogen chloride? Well, you have a periodic table that can help you out with that. It looks something like this. If you don't know where this is, I definitely have it for the test. It would be very helpful. So, hydrogen is 1.01, chlorine is 35.45, so this is 36.46 grams. So to find out how many moles this is, well, that cancels and that cancels. We have 5 divided by 36.46. Your handy-dandy calculator can be helpful. And once again, we could have this for the test. That gives us about 0.137 moles of HCl. So that's how many moles of this we have. We need to do the same thing to this one now, so we can have numbers to compare. So, 10 grams of calcium hydroxide. We're going to multiply it, same exact setup as over there. 1 mole of this on top, and we know how many grams the molar mass of this is. Well, calcium is 40.08, and we got 2 oxygens. Oxygen is 16, so 2 of those is 32. We have hydrogen. Hydrogen is 1.01, there's two of them, so that's 2.02. That gives you a molar mass of about 74.1 grams. So now we have units to cancel. 10 divided by 74.1. So 10 divided by 74.1 gives you moles of about 0.135 moles of calcium hydroxide. These are really close together. Incredible. The thing is though, this is less than this. So this right here is the limiting reagent. Any math, any stoichiometry you do from there works with the limiting reagent. You have to be able to find the limiting reagent first. Has to be the first step. If you have a situation with just one reactant, one reagent, then hey, that's the only reagent you have to work with. You don't have to worry about it. If you have a situation where you only have an amount of data on one of the reagents, that's fine, you're good, you don't have to do this step. But anytime you have multiple reagents, multiple amounts of them, you have to figure out which one to work with. If you just randomly pick one, you could have picked this one. And what you're going to end up with is answers that give you false information. You're never going to use up all the excess reagent. You're only going to use up all the limiting reagent. This holds you back. When you get out one of these moles right here, it's over. So let's say I want to continue this on. What if in this situation I asked you, how much calcium chloride can you make? How many grams of calcium chloride can you make? I'm going to erase this. Beauty of videos, so you can pause this and look at it if you'd like. There it is. Make some room here. Okay. So we're going to start with our limiting reagent. I've already got it in moles. That's beautiful. 0.135 moles of calcium hydroxide. And let's once again say I'm looking for grams of calcium chloride. That's what I'm trying to find. Well, ladies and gentlemen, what we need to do is convert from here to there. We're already in moles here, so whatever's on this line goes in the denominator. When we're at this step, ladies and gents, don't forget, this is the step wherein you have to have moles of the other substance up here. What other substance? The one we're going for, CaCl2. I would call that our target substance. I had to come up with a term for it. Now you're wondering what numbers to put here? Let's look at it. From our equation, we only have 1 mole of CaOH2 and 1 mole of CaCl2. Well, that works out. 1 over 1. These units cancel. What we have left is moles of calcium chloride. We're looking for grams of calcium chloride, so we're going to go on and dig one more step. We're going to go from moles of this to grams of this. That involves molar mass. We've done this before. So, just to get your grams of calcium chloride, I'm going to erase this to make a little more room. This will go on top. This is our target we're going for. And whatever's up here has to go down here. Remember, molar mass is what we're going to use to go from moles to mass. So 1 mole of this gives us how many grams? We use our periodic table. Calcium is 40.08 plus chlorine is 35.45. Put this in right. And there's 2 of those, so it would be plus 70.9. Type that all together, we end up with a nice, lovely number of about 110.98 grams. Cancels with that. Now we have a math problem. 110.98 times 0.135 us 14.983 as our molar mass. 8.2. We'll round it off right here. So, ladies and gentlemen, that is how many grams you can make from this situation. Once you have to use the limiting reagent, you can't use the excess because then we end up with a bigger number that we're never going to get to. This is the absolute most you can make based on limiting reagent work. This limiting reagent idea can be applied to any problem we do. Everything we worked on this year always stipulated what you started with. Now we're going to see, you have to figure it out. That's what limiting reagent work does. So it's limiting reagents. You can apply that, and there'll be at least one problem in the test that actually merges these ideas together in one. So let's look at another situation, this time with percent purity. Percent purity is a step at the beginning of a problem, okay? You start off with a percent of this. Not many things are pure. Whether it be jewelry, whether it be rocks, you name it. Things usually aren't pure. So, let's start off with an impure situation right now. What if we solve this? Speaking of jewelry, let's solve zirconia. Let's say I gave you this problem. ZrSi04 plus this. I'm going to want to balance it for you to save a little bit of time. You have this plus ZrCl4 plus SiO2 plus O2. Ladies and gents, so that's our formula. There we are. Our equation is this. Let's say I gave you, I don't know, somewhere in the neighborhood of 100 grams of 75% chlorine. What that means is this, ladies and gentlemen. What I gave you, 100 grams of it, was not pure chlorine. It was 75% chlorine. So, we need to figure out what actual mass was chlorine. 100 grams. What is 75% of 100? Ladies and gentlemen, don't forget, this is percent purity. In percent purity problems, you take the percent purity times the total mass, and that gives you the pure mass. Say that again. Percent purity, whatever it is, in this case right here, times the total mass, which is right here, gives you the pure mass. So 75% of 100. Any percentage can be written as a decimal. This will be 0.075. Let's move the decimal point 2 times. 100 times 0.075 is 75 grams. That's the actual amount of chlorine you got, that you're starting with. The other 25 grams, who knows what? It doesn't matter what it is. So that is going to be our starting value. That's what we're going to start all our problems with. So let's say I was asking you how many liters of oxygen gas can we make? Put that here so don't forget. If we start with this, which is 75% of 100, we're going to set it up thusly. And I'm going to change colors here to emphasize that this is another step here. 75 grams of chlorine, that's what we just figured out. That was the percent purity part of it. A step before the stoichiometry and conversion and all that. We need to go to moles. When we do anything, we have to go to moles every single time. Since we're going to moles, I'll put it up here. Whatever's up here has to go down here. We need the molar mass of chlorine. Chlorine is 35.45. That's 70.9 then, since there's 2 chlorines. This is the molar mass of a diatomic chlorine molecule. Now, moles of chlorine. We're trying to get to liters of oxygen. The only way, remember, that we can compare two different elements or compounds or molecules of any type is using moles. So whatever's here goes here. We're going to compare this to moles of oxygen, since that's our target. That's where we're going. We use our equation here at this point. 2 moles of chlorine, and we have 1 mole of oxygen. Using coefficients, that's all we do. We've done this before. The previous videos on this, you need more look at that. So this cancels. What we have left is moles of oxygen. We're looking for liters. We're close. Remember, 1 mole of anything, including oxygen gas, at standard temperature and pressure, STP, which is what we're going to be working with in here. We're never going to change off of that. It's always 22.4 liters. So, now we got a math problem. 75 times 22.4 divided by the 70.9 and 2. So your handy calculator can help you with this. 75 times 22.4 divided by 70.9 divided by 2. That gives you 11.8 liters of oxygen. There you go, ladies and gentlemen. That is how many liters of oxygen you have in this situation. How many could be made? That was our product. How much was made based on our impure sample? We had to figure out how much was pure at the beginning. Because remember, we had 100 grams of chlorine, 75% chlorine. You had to find 75% of 100. That's 75. Easy math for this example. And then we converted it to moles of chlorine, because moles are our central unit. We use the moles of chlorine to compare to moles of oxygen. Then we use moles of oxygen to go to liters of oxygen. 22.4 is the number you need to be familiar with. 22.4 liters is 1 mole at STP every single time. Every single time. So, that is that one, percent purity. Let's do one more, percent yield. Here it is, I'm going to erase it. Well, percent yield. Percent yield is a after-the-fact situation. It's a product situation. It's one where percent purity had to figure out what to do with the reactants. Percent yield is something we do after the fact. It goes something like this. What if we had, let's go with this. We have some zinc sulfide plus some oxygen gas yields some zinc oxide plus sulfur dioxide. Alright, ladies and gents, first thing you notice, this is imbalanced. So, for instance, you might need to get 3 oxygens here, 2 oxygens there. We're going to need to increase. What if I put a 3 there? That gives us 6. Sounds good. If I do that and I put a 2 right there, that almost solves our oxygen problem. Put a 2 there. Now my oxygen's all clear, all balanced. We got 2 sulfur, 2 zinc. I put a 2 right there, all balanced. Now we're good. And I'm going to put a line through my Z's so you can tell from the zinc. So my 2's and my Z's are very similar. Now, here's where the percent yield part comes in. What if I told you that we start off with, let's say, 50 grams of zinc? Here's how we do this. We're trying to find how much, what's sulfur dioxide? How much of this? Grams of sulfur dioxide. We need to go to moles first. We need the molar mass of zinc. There's 1 mole goes here. Those lines in there. Okay. you'll check your handy dandy periodic table, is 65.38. That cancels. Now, 2 moles of zinc over there from our board. Except for it's, ladies and gentlemen, I've made an error. Please forgive me. This is zinc sulfide. I left off an important piece of this. I forgot the sulfur part. Please forgive me. Nobody's perfect. So I'll go from here to there. Let me start this over. So, grams of zinc sulfide for 1 mole of zinc sulfide. We need to find the molar mass of zinc sulfide. We just said zinc is 65.38. Well, sulfur, ladies and gentlemen, is 32.07. So that gives us 97.45. Much more rational here, okay? Now, over here, we have 2 moles of zinc sulfide. And we're going for sulfur dioxide, so there's 2 here. Well, look at that. That works out beautifully. Clean that up a little bit. Sorry, guys, miswrote. This is 2 moles of sulfur dioxide. Now, we're needing to go to grams of sulfur dioxide. So, we're trying to get to grams of sulfur dioxide. We'll need to use molar mass. Move this out of the way so we have more room. We have 1 mole of sulfur dioxide is how many grams? Well, we just said that sulfur is 32.07. 2 oxygens would be 32. It's 16 for oxygen, 2 of them. 64.07 grams sulfur dioxide. We're at the end, so in your math, 64.07 times 50 times, well, our 2's cancel. So don't worry about that even. And divide it by 97.45, which is right there. That gives us this right here. 32.8, say 32.8 grams. Here's where percent yield comes into play, ladies and gentlemen. In any word problem that you see like this, it'll mention something along the effect, something to the words of the effect of, oh, you did this reaction, and, sorry, one sec, guys, I'll clear this out of the way. You did this reaction, and you only produced 15 grams of this. It'll say something like that. You were able to produce, you made, you generated so many, whatever. 15 grams. It's stipulated as part of the problem. It'll be given to you. You'll have to come up with that. Here's how you'll use it, though. What we just found, this amount right here, we call this our theoretical yield. This is theoretical. All of our math all year long has been theoretical. All of this we've been doing for months now is theoretical. It does not deal with the problems of reality where things don't always work out perfectly. So, this is theoretical. We want to see what percentage of this theoretical amount we were actually able to get. That is what percent yield is. So, I'm going to erase this so I can show you. Percent yield, ladies and gentlemen, if you had to write a formula, looks something like this. This is straight in your book. It is the actual yield over the percent yield. Actual yield divided by percent yield. Oh, excuse me. I'm tripping up here, ladies and gents. Please forgive me. Over theoretical yield. what you actually got divided by what you should have gotten. It'd be wonderful if this were 100%. In reality, it's not often, almost never. Our actual yield is what I stipulated, what I gave you in the problem. 15 grams. Divided by our theoretical yield, 32.8 grams. So, actual yield, percent yield goes this way. 15 divided by 32.8. That gives us a number of 0.457. That's our theoretical or percent yield. We could write that as a percentage, 45.7%. Either way of writing this is acceptable. Either way. The thing is, this is decimal, this is a percentage, it means the same thing. So just write it one way or the other. What we found was how effective our experiment went. It was a 45% of what we should have gotten, almost 46. Not great, we could probably do better. Closer to 100 is obviously better. So this is percent yield. How much did we actually get compared to what we should have gotten if everything went perfectly? So ladies and gentlemen, we've gone over limiting reagents, which tells you what reagent you have to work with to start every problem. In these two last examples I gave you, I stipulated what the